Hello everyone. Today we will be learning about magnetic fields and in particular their effect on charged particles both qualitatively and quantitatively. Now you've already learned a little about magnetic fields, so just a quick review. Magnets are surrounded by magnetic fields. Magnetic field lines, which represent the fields, point from the north pole of the magnet to the south pole of the magnet, as we can see here. And finally, a current-carrying conductor in a magnetic field experiences a force, which we learned about in the motor effect. Now, in the motor effect, we use the right-hand rule to find out the force of the conductor in a magnetic field. We can use the same thing to find the force of a charged particle in a magnetic field. So once again, the fingers of the hand represent the direction of the magnetic field. The palm represents the direction of the force. But the thumb can't represent current because charged particles don't have current. So instead, the thumb points to the direction of the positive charge velocity. That means if the charge is positive, then the thumb will point in the same direction as the charge's motion, whereas if the charge is negative, the thumb will point in the opposite direction of the charge's motion. Now, the force on a current-carrying conductor is given by F equals BIL sine theta. Now, a charged particle doesn't have a current or a length, so instead it must have a different formula. We find that the force on a charged particle, moving with a velocity v, is given by F equals qvb sine theta. Now, because there's a v in this equation, if the particle is not moving, it will not experience a force, just like a current-carrying conductor without a current does not experience a force. And in fact, the force will change the direction that the particle is moving in, which, of course, will change the direction of the force as well. So we can see that at the top of the board here, if we use the right-hand rule, we can see that the particle will experience a force downward, and this will change its direction. When it's moving downward, the force will, of course, be in a different direction. If we look at this from a different perspective, we can see that the charged particle, when it enters a magnetic field, is moving in a circle. And so as long as it enters at right angles to the field, it will follow a circular path at constant speed. So here we have an animation. When the charged particle is moving upward, we can use the right-hand rule to see that it experiences a force towards the middle of the circle. Whereas when the particle is moving downward, the force it experiences again will be in a different direction, but again toward the middle of the circle. Now, because we're working with an object traveling in a circle, we can use centripetal force to describe it, which of course I'm sure you all remember from year 11. So the equation for centripetal force is F equals mv squared on r. We also know that the strength of the force acting on this particle is given by qvb. So by equating these two, we can find out a few things about the path that the particle is moving in, particularly its radius. So here we have qvb equals mv squared on r. We can start by dividing both sides by v to get rid of the squared. Next, we can divide both sides by qb and multiply by r, which gives us the following equation. R equals mv over qb, which is also seen here. So this means that when a charged particle is traveling in a circle due to a magnetic field, the radius of its path it increases when it's heavy or when it's moving fast, and it decreases when the field has a strong charge on it or when the magnetic field is very strong. Now, when a particle enters a magnetic field but not at right angles, it'll move in a spiral pattern or a helical path. So why could this happen? Well, we can break up the motion of the particle into two different components. One moving parallel to the magnetic field and one moving perpendicular. Now we know that when a charged particle is moving in the same direction as the magnetic field, it does not experience a force. So this will have no effect on the path of the particle. Whereas the part that's moving perpendicular will cause the particle to move in a circle. So the net effect is that there's circular motion here, but with a constant velocity in this direction, which means that the particle follows a spiral path or a helical path. And in fact, we can see this in nature. When charged particles come at us from the sun, they interact with the Earth's magnetic field. They don't come in straight at right angles, so they follow a helical path and follow the line of the magnetic fields to the poles. And this protects the Earth from being struck by these charged particles, which might otherwise be damaging to us. And when the beams of particles interact with the atmosphere of the Earth, they produce colourful aurorae. This concludes the theory. We have learned about the qualitative and the quantitative effects of magnetic fields on charged particles and the paths that the charged particles take. Now let's go on to some questions. Question 7. A negatively charged particle travelling from left to right enters a magnetic field and is deflected towards you. What is the direction of the magnetic field? Now we can use the right-hand rule in this instance. The negatively charged particle is moving from left to right in this plane. The magnetic field is towards you, and so right angles must mean that the particle is deflected upwards or downwards. So right away we can see that it's not towards you, because that means that it will be deflected in the direction of the magnetic field. We can tell it's not moving away from you because we'd encountered the same problem. So it's neither A nor B. So it's either upwards or downwards. Now if the particle is moving from left to right, our thumb's here, and the magnetic field is towards you, the deflection is towards you, the direction of the magnetic field must be upwards. But this only works if the particle is positively charged. If it's negatively charged, then this isn't the case. So the answer can't be upwards. We find that the positive charge velocity is in fact the other direction, from right to left. And so, if the field is deflected towards you, the magnetic field must be pointed downwards. And we find that D, downwards, is the correct answer. Question 8. Which of the following changes would increase the radius of a charged particle's path in a magnetic field? Now we can recall that the radius of the particle's path is given by r equals mv over qb. So let's consider our options. Increasing the size of the magnetic field. Well, we can see that if the magnetic field is very great or very small, as long as it's the same strength, it won't affect the path of the particle. So D can't be the right answer. Alright, well let's consider A, increasing the strength of the magnetic field. We can see that because it's part of this equation, it will change the radius of the particle, but increasing it will in fact decrease the radius of the particle. So A is not the right answer either. Well, what about B, increasing the magnitude of the particle's charge? Once again, the charge is on the bottom of the equation, so if we increase this, the radius will decrease. This can't be the right answer. Our last option is C, increasing the velocity of the particle. We can see that if the velocity increases, the radius of the path that the particle is taking will also increase, and so C must be the right answer. Centripetal force is always useful when dealing with objects moving in a circle. On to question 9. Alpha radiation consists of positively charged particles. Suppose some alpha radiation, moving from left to right, enters a magnetic field. The magnetic field lines point towards you, so what is the path that the positive radiation will take? Well, we can use the right-hand rule to figure this out. The positive particles are moving from left to right, so the positive charge velocity is in the direction of the thumb, left to right. If the magnetic field is pointing towards you, then the particles will experience a downward force, and so will follow a curved path, something like this. Question 10. A beam of electrons travels in a circular path in a magnetic field. The electrons have a charge to mass ratio here. The beam's path has a radius of 5 millimeters. Now, if the magnetic field has an intensity of 1,000th of a Tesla, then how fast are the electrons moving? The relevant equation here is R equals mv over qb. because, of course, we have a radius of circular motion. Now, of course, we have to convert these millimeters into meters before we can substitute them in for the radius. And it's difficult to put in the charge to mass ratio unless we know what that means. So it is, of course, Q over M, and the charge to mass ratio is substituted for both Q and M. The magnetic field strength is, of course, just substituted for B. After putting these values into the equation, it becomes something like this, where, of course, 5 millimeters has become 0.005 meters. Rearranging the equation, we have this expression, which allows us to find the speed of the particle being 1.76 times 10 to the 6 meters per second. Finally, we have question 11. Two parallel metal plates in a magnetic field are separated by a distance d. An electron enters the space between the plates. So, in which direction does the force in the electron point due to the magnetic field? We can use the right-hand rule to figure this out. The electron is moving in this direction, but because it's a negatively charged particle, the positive charge velocity is in the other direction. If the magnetic field points into the board, that means the force that the electron experiences is downwards. And we can see that downwards is indeed the answer. Part B. The electron has this charge. The strength of the magnetic field is 0.001 Tesla, and the electron's velocity is here. Calculate the magnitude of the magnetic force on the electron. The relevant equation in this case is F equals QVB. We can substitute the charge as Q, the velocity as V, and the magnetic field intensity as B. After doing this, the equation looks something like this. We can use a calculator to evaluate this expression, and we find it to be 3.2 times 10 to the minus 16 newtons. Now this might seem like quite a small force, but remember, the electron is a very small particle, and so this is in fact quite substantial. Finally, part C. Calculate the strength of the electric field between the plates if the electric force balances the magnetic force. Now, the relevant equation here is F equals QE, which, as we know, is the force on a charged particle in an electric field. Now, all we have to do is equate this force with the force we calculated in the previous part of the question to find, which is here, to find an expression for the electric field strength. Dividing both sides by this number, we calculate an expression for E, and evaluating that, we find that the strength of the electric field is 2000 volts per meter. This is the end of this section. In this section, we have learned the effects of magnetic fields on charged particles, both qualitatively and quantitatively, and the paths that the charged particles follow.